So, here is something I want you to think about as you settle in tonight. Hold your hand up in front of your face. You can do it in the dark. You do not need to see it. Just hold it there, a few inches from your nose. Now, between the tip of your finger and the tip of your nose, there is a gap. Maybe 3 or 4 inches of empty air. And here is the question. What is in that gap? You might say nothing. Air, sure, some molecules of nitrogen and oxygen bouncing around, but essentially nothing. Empty space, a void. And for most of human history, that is exactly what people believed. The space between things was just absence. It was the place where stuff was not. If you wanted to push something, you had to touch it. If you wanted to pull something, you had to grab it. Force required contact. That was the deal. That was how the world worked.
But then, about 2,500 years ago, someone picked up a dark, rough stone near a city in what is now Western Turkey, held it close to a small piece of iron, and the iron jumped. It leapt across that gap, across that supposedly empty nothing, and stuck. No hand pushed it, no string pulled it. Something invisible, something hiding in the space between, had reached out and grabbed it. And tonight, I want to tell you the story of what that something turned out to be. Because that invisible presence lurking in the gap between the stone and the iron turned out to be one of the most important things in the entire universe. It turned out to be the reason light exists, the reason your phone works, the reason your heart beats, the reason you can see and hear and think. It turned out to be woven into the fabric of reality so deeply that without it, atoms would not hold together, chemistry would not happen, and you would not be here, lying in the dark, listening to this.
And the story of how we figured all of that out, how we went from "that is a weird rock" to "the universe is filled with an invisible architecture that governs nearly everything," that story stretches across 25 centuries. It involves philosophers who thought stones had souls, a physician who carved magnets into tiny earths, a bookbinder's apprentice who had almost no formal mathematical training but saw things no professor could see, and a quiet Scottish mathematician who, working alone with pen and paper, predicted the existence of something no human had ever detected, and turned out to be exactly right. And that invisible something is passing through your body right now. It is holding every atom in your hand together. It is carrying the warmth radiating off your skin. It is running through the nerves that let you feel the weight of your own head on the pillow.
Without it, your hand, the pillow, the room, all of it would dissolve into a cloud of loose particles with nothing to bind them. And you have never once noticed it is there. So here are the questions I want us to sit with tonight. What is actually filling the space between a magnet and the iron it pulls? And why is that same invisible something holding your body together right now? Is what we call empty space truly empty? Or is something hiding there? Something real? Something that carries energy and exerts force, and has been doing so since long before anyone knew to look? How did we go from a world where forces seem to teleport magically through nothingness to a world where we understand that space itself is alive with invisible structure? And what does that invisible structure have to do with the light in your room, the signal in your phone, the electrical impulse running through your nerves at this very moment, as your brain turns these sounds into meaning.
Those are big questions. And the answers, when they finally came, changed everything. Let us start at the very beginning, with a rock. About 2,500 years ago, give or take, people living along the coast of a region called Ionia, in what is now Western Turkey, noticed something peculiar about certain stones found near a city called Magnesia. These stones were dark, heavy, rough to the touch, and they had a property that no other material seemed to have. If you held one of these stones close to a small piece of iron, the iron would move toward it. It would slide across the table, or lift off the ground, or cling to the stone as if glued. No other rock did this. You could hold a piece of granite next to iron all day, and nothing would happen. Limestone, marble, sandstone, nothing. But these particular stones, these dark, dense pieces of what we would now call magnetite, a mineral made of iron and oxygen arranged in a very specific crystal structure, these stones could reach across empty space and pull. The Greeks called them lithos magnetus, the stones of Magnesia. And that is where the word magnet comes from. Just a place name. It stuck for 3,000 years. Now, think about what this must have looked like to someone in the ancient world. They understood forces pretty well on an intuitive level. You push a rock, it rolls. You pull a rope, the bucket comes up from the well. You throw a spear, it flies through the air until it hits something or falls. Every force they had ever encountered required contact. Something had to touch something else to make it move. But here was a stone that could cause motion without touching. The iron was sitting on the table, perfectly still. And then it moved, drawn by an invisible hand reaching out from the rock, reaching through what appeared to be empty air. Something was happening in the space between the stone and the iron. Something you could not see, could not hear, could not smell or taste, but you could feel it. If you held the iron close and slowly pulled it away, you could feel a resistance, a tug, as though the air between them had become thick, had become something. This was, in a very real sense, the first time human beings encountered what we would eventually call a field, an invisible influence extending through space. But nobody used that word. Nobody even had a concept for it. All they knew was that these stones were strange, and possibly a little magical. Thales of Miletus, one of the earliest Greek philosophers, born around 624 BCE, apparently thought the lodestone must have a soul, and honestly, given what he had to work with, that was a perfectly reasonable guess. In his framework, spontaneous motion, motion that started on its own without something else pushing, was a characteristic of living things. Animals move on their own, plants grow on their own, dead objects just sit there unless something alive pushes them. But here was a stone, clearly not alive by any normal measure, that could cause motion. So either the rules were wrong, or the stone was in some sense alive. Thales went with option 2. He was wrong, of course, but he was wrong in an interesting way. He was grappling with a genuinely deep problem, the problem of action at a distance, the problem of how one thing can influence another without touching it. And that problem would haunt physics for the next 2,500 years, right up until the answer finally came from the most unlikely of places. Other Greek thinkers tried their hand at explaining the lodestone. Lucretius, the Roman poet and philosopher who lived around 50 BCE, proposed a mechanical explanation. He suggested that the lodestone emitted a stream of tiny particles that pushed the air out of the space between the stone and the iron, creating a sort of vacuum, and the iron rushed in to fill that empty space. It is completely wrong in its details. There are no streams of particles being emitted, and the mechanism has nothing to do with vacuum pressure. But notice what Lucretius was doing. He was trying to explain action at a distance using only things he already understood, contact forces and particles. He was trying to get rid of the mystery by proposing a mechanism. And that instinct, the instinct to replace "it just does that" with "here is how it works," that is the beginning of physics. That is the impulse that eventually leads to electric motors, MRI machines, and the phone sitting on your nightstand.
But for a very long time, that impulse did not go very far with magnetism. The lodestone remained mostly a curiosity, wrapped in superstition and folklore. People in the medieval period thought lodestones could cure headaches, or that garlic could demagnetize them, or that placing a lodestone under a sleeping person's pillow could test their faithfulness. There is a wonderful legend from the Middle Ages that the tomb of Muhammad was suspended in mid-air by the power of lodestones embedded in the ceiling and floor. It is not true at all, but it tells you something about how powerful and mysterious people found even the idea of magnetic levitation, even as a fantasy. And here is where I want to slow down and underline something, because it matters for the rest of the story. The thing that made magnetism so strange, so unsettling, so resistant to explanation, was not the force itself. Forces were everywhere. People dealt with forces every day. The strange part was the gap, the empty space between the lodestone and the iron. Something was reaching through that gap, and nobody could say what it was. The force was invisible. The mechanism was invisible. The medium, if there even was one, was invisible. That gap, that invisible something lurking in empty space, is the thread we are going to follow tonight. Because it turns out that figuring out what fills that gap, what is actually happening in the space between a magnet and the thing it pulls, was one of the deepest, most consequential puzzles in the entire history of science. And the answer, when it finally came, revealed that empty space is not empty at all. It is full. Full of something real, something measurable, something that carries energy and transmits force and makes the universe work. But we are getting ahead of ourselves, because before anyone could figure out what was in the gap, something else had to happen first. Someone had to realize that this mysterious lodestone force was not the only invisible reach in town. There was another one. And it had been hiding in plain sight, quite literally under people's noses, for just as long. Around the same time that Greek philosophers were puzzling over lodestones in Magnesia, they noticed something else entirely. Something that seemed to have nothing whatsoever to do with magnets. If you took a piece of amber, that golden, translucent, fossilized tree resin that the Greeks prized for jewelry and decoration, and rubbed it briskly against a piece of fur or wool, it could attract small, light objects. Bits of straw, tiny feathers, specks of dust. They would leap toward the rubbed amber and cling to it, as though grabbed by invisible fingers. The Greeks called amber electron. And that word, that ancient Greek word for a pretty piece of fossilized tree sap, is where we get the word electricity. Now, if you were an ancient Greek, watching amber pull straw and lodestones pull iron, you might reasonably think these were the same phenomenon. Both involved invisible forces reaching across gaps. Both involved attraction without contact. Both seemed equally mysterious. And for a very long time, people did lump them together in a vague category of strange things that pull other things without touching. But there were differences. Subtle differences that nobody paid much attention to for over 2,000 years, but differences that would eventually turn out to be enormously important. The lodestone attracted iron all the time, without any preparation. You did not have to rub it or warm it or do anything to it. It just worked. The amber, on the other hand, only attracted things after you rubbed it. Leave it sitting on a shelf and it does nothing. Rub it on fur and suddenly it can pull. Also, the lodestone only attracted iron and a handful of other specific metals.
The amber, once rubbed, could attract many different materials: straw, feathers, bits of paper, all sorts of lightweight things. And if you put a thin sheet of paper between a lodestone and a piece of iron, the iron still moved. The magnetic force went right through the paper as if it were not there. But the amber's attraction was more delicate, more easily disrupted. Two invisible forces, both reaching through gaps, both causing motion without contact, but behaving differently in important ways. Were they the same thing wearing different masks? Or were they genuinely different phenomena? For 2,000 years, nobody seriously investigated the question. Magnetism was a curiosity. The amber effect was a curiosity. And curiosities do not build civilizations. But there was one application of magnetism that was anything but a curiosity. One use that would change the world long before anyone understood why it worked. And that use was navigation. Sometime around the 1st or 2nd century of the Common Era, and the exact dates are genuinely debated among historians, so I will be honest about that. Chinese scholars discovered that if you carved a piece of lodestone into the shape of a spoon and placed it on a smooth bronze plate, it would rotate until the handle pointed south. They called it a south-pointing spoon. Whether this was initially used for practical navigation or for ritual divination is a matter of some scholarly argument. But the key insight was extraordinary. This stone knows where south is. It has a directional preference that is consistent, reliable, and somehow connected to something much larger than itself. By around the 11th century, Chinese navigators were definitely using magnetized iron needles, not lodestones themselves, but iron needles that had been stroked against a lodestone to transfer the magnetic property, floating on water or suspended by a silk thread, as actual compasses for ocean navigation. And this changed everything. Before the compass, if you were sailing out of sight of land on a cloudy night, you were essentially guessing. No stars visible, no landmarks, nothing to orient by. You were alone on a featureless ocean with no way to know which direction you were heading. The compass gave sailors an invisible thread, connecting them to the geometry of the Earth itself. It took voyages that were suicidal and made them merely dangerous. It took trade routes that were seasonal and made them year-round. It made the world smaller. And the compass did something else, something harder to measure, but equally profound. It changed how human beings related to the invisible. Before the compass, the forces you dealt with were tangible. You could feel the wind. You could see the stars. You could taste salt spray and feel the swell beneath the hull. Navigation was sensory. It relied on things you could perceive directly. The compass introduced something different. It gave you access to information that your senses could not detect. No human being can feel the Earth's magnetic field. You cannot see it, hear it, smell it, or taste it. It passes through your body continuously, and you have no awareness of it whatsoever. But the compass needle can feel it. The compass extends your perception into a realm that is completely invisible to your unaided senses. And once you accept that there is real, reliable,
useful information carried by a force you cannot perceive, you have taken the first step toward the modern scientific worldview. The universe is full of things you cannot see, but that are nonetheless real and measurable. Magnetic fields,
Electric fields, radio waves, ultraviolet radiation, neutrinos, dark matter. The history of science is largely the history of building instruments that extend human perception into invisible realms. And the compass was one of the first. There is a detail about early compass use that I find particularly striking. Chinese navigators did not always use the compass the way European navigators later would. In some early Chinese texts, the compass is described as a tool for confirming your direction, not for discovering it. The navigator would have a general sense of direction from the wind, the waves, the stars, the flight patterns of birds, and the compass would serve as a check, a quiet confirmation that you were heading the right way. It was a conversation with the invisible, not a dictation from it. European navigators, especially after the 15th century, came to rely on the compass more absolutely. They used it as a primary navigation tool, not a secondary check.
And as they did, they noticed things that Chinese navigators may have noticed but did not emphasize. The declination problem, for instance. The compass does not point exactly to true north. There is an offset, an angle between magnetic north and true north, and that angle varies depending on where you are on the Earth's surface. Columbus noticed this crossing the Atlantic. It alarmed his crew. They were sailing into unknown waters, and now their most reliable instruments seemed to be lying to them. Columbus calmed them by pointing out that the compass was still consistent, that the offset was predictable, and that they could correct for it. He was practicing empirical science, trusting measurement and pattern over theory and fear. The declination, far from being a flaw in the compass, turned out to contain information about the Earth's magnetic field. Mapping declination across the globe became a major scientific project in the centuries that followed, and the patterns that emerged provided clues about the structure of the Earth's interior that geologists would not fully understand until the 20th century. The compass reached Europe probably around the 12th century, likely through Arab trade networks, though the exact path is murky. And European sailors adopted it immediately. But here is what I find fascinating. For centuries, people used the compass without having any real understanding of why it worked. They knew the needle pointed north. They knew it was reliable enough to bet their lives on. But they did not know what it was responding to. Was it the North Star, pulling on the needle from above? Was there a giant mountain of lodestone somewhere near the North Pole? That was actually a popular theory. Some map makers even drew this imaginary magnetic mountain on their charts, sitting up near the pole, quietly pulling every compass needle in the world toward it. And this is a pattern you see again and again in the history of technology. Practical use runs way ahead of theoretical understanding. People navigated entire oceans for 300 or 400 years using magnetism before anyone did a serious scientific study of what magnetism actually was. The engineering came first. The science came later. We like to pretend it works the other way, that scientists figure things out in labs, and then engineers apply the knowledge. But historically, it very often goes in reverse. Someone builds a thing that works, and then, sometimes centuries later, someone else figures out why. The person who finally sat down and did the serious work was an English physician named William Gilbert. And Gilbert is one of those figures in the history of science who deserves to be far more famous than he is.
He was born in 1544 in Colchester, England, studied at Cambridge, became a successful doctor, and eventually served as personal physician to Queen Elizabeth I. But his real passion was not medicine. It was natural philosophy, what we would call science. And he spent nearly 20 years, 2 full decades, conducting careful experiments on magnetism and electricity before publishing his masterwork in 1600. The book was called De Magnete, On the Magnet, and it is one of the most important scientific texts ever written. What makes it remarkable is not just the conclusions Gilbert reached, but the way he reached them. He did experiments, careful, repeatable, methodical experiments. In an era when most natural philosophers were still arguing about what Aristotle had said, or what ancient texts implied, Gilbert was actually testing things. He built his own instruments. He tried different materials. He recorded what happened. And when the results contradicted the old authorities, he went with the results. Here is what Gilbert did that was so brilliant. He carved a lodestone into the shape of a sphere. He called it a terrella, a little earth. And then he took a tiny compass needle and mapped how it behaved at different positions around the sphere. He moved the compass to the equator of the terrella, to the poles, to every point in between, and he carefully noted what happened. And what he found was extraordinary. At the equator of the little sphere, the compass needle lay flat, pointing along the surface. But as he moved the needle toward the poles of the sphere, it began to tilt. It angled more and more steeply downward, until right at the pole, it pointed straight down, perpendicular to the surface. And this matched exactly what real sailors had been noticing on real voyages. As you sailed further north, the compass needle developed an increasing tendency to dip toward the ground. Gilbert's little sphere was reproducing the behavior of the entire planet in miniature. From this, Gilbert drew his great conclusion. The Earth itself is a giant magnet. That is why compasses point north. Not because of a magnetic mountain, not because of the stars. The whole planet, this enormous ball of rock and water, has a magnetic field, with a north pole and a south pole, and the compass needle simply aligns itself with it. This was a genuinely radical idea in 1600. He was saying that the Earth had an invisible influence extending out from it into space, reaching every compass needle on its surface. It was one of the first times anyone had proposed a truly global, planetary-scale, invisible phenomenon and backed it up with experimental evidence. Now, Gilbert also did something else that matters enormously for our story, even though it seems like a small thing at first. He drew a clear, careful distinction between magnetism and electricity. See, people had been lumping the lodestone effect and the amber effect together for centuries. Lodestones attract iron. Rubbed amber attracts straw. Seems like the same thing. Gilbert said no. He systematically tested the differences. He showed that magnetism works only on iron and a few specific materials, while the amber effect, what he called the electric force, works on many different substances. He showed that magnetism does not require preparation. A lodestone is always magnetic, while amber only attracts things after it has been rubbed. He showed that magnetic force passes through barriers like paper or cloth, while the electric force is more easily disrupted. By separating these two forces so clearly, Gilbert did something he could not possibly have foreseen. He set the stage for one of the greatest surprises in the entire history of physics, a surprise that would not come for another 220 years, because those two forces, the magnetic and the electric, which Gilbert had so carefully separated, turned out to be two faces of a single, deeper phenomenon. And the person who stumbled onto that connection was not even looking for it. But before we get there, something important has to happen first. Electricity, which for 2,000 years had been nothing more than the amber trick, a parlor curiosity, has to become a subject of serious study. It has to grow up. And the story of how that happened is a wild one, full of sparking machines, electrified boys, jolted soldiers, and a printer from Philadelphia who would fly a kite into a thunderstorm and live to tell about it. So let us move forward in time, past Gilbert, past the compass and the Torella, into the 17th and 18th centuries, when electricity stopped being a curiosity and started being a force people could actually harness.
Because the story of the field, the story of that invisible something hiding in empty space, cannot be told with magnetism alone. It needs electricity too. And electricity was about to have its moment. In the 1600s, after Gilbert, the study of electricity began to pick up momentum, slowly at first, and then with increasing energy. And the early electrical experimenters were, honestly, kind of wild. This was the era of spectacular demonstrations, of traveling showmen, of occasionally dangerous stunts performed in front of paying audiences, all in the name of understanding this mysterious force. One of the key developments came from a German named Otto von Guericke, who around 1660 built what is generally considered the first electrostatic generator, and the device was wonderfully simple. It was a ball of sulfur, about the size of a child's head, mounted on an iron shaft so it could be spun. Von Guericke would spin the sulfur ball and press his dry hand against it, and the friction would build up a charge on the surface. He could then bring the charged ball near small objects and watch them leap toward it. Or he could draw tiny sparks from it with his finger. It was crude, but it was the first machine that could produce electricity on demand, rather than just rubbing a piece of amber by hand. And that is a meaningful leap. You are going from passively observing a natural curiosity to actively building a device that creates the effect deliberately and repeatedly. That is the beginning of engineering. Von Guericke also noticed something that must have been startling. He found that the attractive force could be transmitted along a linen thread. If he connected his charged sulfur ball to a thread and dangled a feather near the other end, the feather would be attracted from a distance. He was seeing electrical conduction. The charge was traveling along the thread. He did not fully understand what he was seeing, but he documented it, and others would build on it. By the early 1700s, the study of electricity had become fashionable. Traveling lecturers toured Europe, performing electrical demonstrations for paying audiences. They would charge up glass tubes by rubbing them with silk, then use them to make sparks fly, make people's hair stand on end, attract bits of paper and gold leaf. One popular demonstration involved suspending a boy from silk ropes and charging him up by touching him with an electrified glass tube. His face would glow faintly in the dark. His hair would stand straight up, and if someone approached with their hand, a visible spark would leap from the boy's nose to their knuckle. Audiences loved it. Around the same time, a French chemist named Charles-François Dufay discovered something genuinely important. He found that there seemed to be two different kinds of electricity. If you rubbed glass with silk, you got one kind. If you rubbed resin with fur, you got another kind. And objects charged with the same kind repelled each other, while objects charged with different kinds attracted each other. Dufay called them vitreous and resinous electricity. This was the first hint that electrical charge comes in two flavors, what we now call positive and negative. And that rule, that like charges repel while opposite charges attract, is one of the most fundamental principles in all of physics. But all of these experiments shared a frustrating limitation. The charges dissipated quickly. You would rub your glass tube, build up a charge, and within moments it would leak away into the air. You could not accumulate it. You could not store it for later. And then, in 1745, everything changed because of an accident in the Dutch city of Leiden. A professor named Peter van Musschenbroek was experimenting with ways to store electrical charge.
He was trying to electrify water inside a glass jar, and his colleague, a man named Andreas Cuneus, was holding the jar in one hand while touching a charged conductor with the other. And what happened next reportedly knocked Cuneus halfway across the room. He had accidentally created a circuit through his own body, and the stored charge discharged through him in a single, violent jolt. Cuneus later said he would not repeat the experiment for the entire Kingdom of France. What they had stumbled onto was the Leyden jar, the very first electrical capacitor, a device that could store charge and release it all at once in a powerful burst. The design was simple. A glass jar coated inside and out with metal foil, with a metal rod passing through the lid. You charged it up by touching the rod to an electrostatic generator, and the charge accumulated on the inner foil, held in place by the glass, with an equal and opposite charge building on the outer foil.
And when you connected the inner and outer foils through a conductor, or through your body, as Cuneus learned the hard way, all that stored energy discharged at once. The Leyden jar was a sensation. People started connecting multiple jars together in what they called batteries. And yes, that is where the word comes from. A battery of jars, like a battery of cannons. With enough jars linked together, you could produce sparks several inches long, ignite gunpowder from across a room, kill small animals. Electricity had gone from a parlour trick to something genuinely powerful and a little bit frightening. And the person who would do more than anyone else to make sense of it all was a printer's son from Boston who had never attended a university in his life. Benjamin Franklin was, by the time electricity captured his imagination in the mid-1740s, already one of the most remarkable people in the American colonies. He had run away from an apprenticeship to his older brother's print shop, made his way to Philadelphia as a teenager with almost nothing, built a printing business, published Poor Richard's Almanac, helped found a lending library, organized a volunteer fire company, and retired from active business at 42, wealthy enough to spend the rest of his life doing whatever interested him. And what interested him, starting around 1746, was electricity. Franklin was not a trained natural philosopher. He had no degree, no formal instruction in physics. What he had was an extraordinarily sharp mind, a gift for clear thinking, and a complete lack of reverence for how things had always been explained. He got his hands on some basic equipment, a glass tube, some Leyden jars, and began experimenting methodically in his own home. And within just a few years, he developed a theory of electricity that was more coherent and more useful than anything anyone had proposed before. Here is what Franklin figured out. He proposed that electricity was a single fluid, not two different types, present in all matter. When you rubbed amber against fur, you were not creating electricity, you were moving it. The amber gained extra fluid, and the fur lost some. He called the condition of having too much fluid positive, and the condition of having too little negative. Those words, positive and negative, that is Franklin. That convention is still used in every circuit diagram, every physics equation, every battery terminal in the world today. Now, Franklin got one thing slightly wrong, and it has confused students ever since. He guessed that the electrical fluid flowed from positive to negative. That seemed logical. But when electrons were eventually discovered about 150 years later, it turned out they carry negative charge and flow in the opposite direction. So conventional current, the way we draw it in diagrams, runs opposite to the actual movement of electrons. It is Franklin's legacy, a convention so deeply embedded that even after we discovered it was technically backward, we just kept using it. But what Franklin got right was far more important than what he got wrong. He understood that electricity is conserved. You cannot create it or destroy it. You can only move it from one place to another. When you charge a Leyden jar, you are not making new electricity. You are redistributing it, pulling it from one surface and piling it up on another. The total amount stays the same. That is conservation of charge, one of the most fundamental principles in physics. And Franklin arrived at it through careful observation in a home laboratory in colonial Philadelphia. Franklin's single fluid theory also gave him a way to understand the Leyden jar that was cleaner than anything anyone else had proposed. Before Franklin, people thought the jar somehow created or stored a special electrical substance. Franklin saw that the jar was simply a device for separating charge that already existed. When you charged the jar, you were pulling electrical fluid from one foil and pushing it onto the other. The glass between them held the separation in place, like a dam holding back water. The total charge in the system never changed. It was just redistributed, pulled apart, held at tension by the insulating glass. This picture made the Leyden jar intelligible for the first time, and it predicted something that Franklin promptly tested. The charge on the inner foil must be exactly equal and opposite to the charge on the outer foil. If you added them together, they would cancel exactly. Franklin confirmed this by discharging the two foils simultaneously and showing that the total charge was zero. Equal and opposite. Conservation of charge. Demonstrated experimentally in a Philadelphia living room by a man with no university education, using equipment he had built himself from materials available in any colonial American city. It is hard to overstate how important conservation of charge would turn out to be. It is one of the cornerstones of modern physics. It holds in every known interaction, from the collision of subatomic particles in accelerators to the largest electromagnetic events in the cosmos. Charge is never created and never destroyed. It can move, it can flow, it can be redistributed, but the total amount in a closed system never changes. And Benjamin Franklin figured this out in the 1740s by playing with a glass jar and some metal foil. Franklin also figured out something subtle about the Leyden jar that surprised everyone. He showed that the charge was not actually stored in the metal foils. It was stored in the glass. You could disassemble a charged jar, remove the inner foil, touch it, nothing. Remove the outer foil, touch it, nothing. But the glass itself retained the charge. Reassemble the jar with fresh foils, and the shock was still there, waiting. The glass, the insulator, was doing the real work. That is a genuinely deep insight for someone working in a home lab in the 1740s. And then there was the kite. The popular image is Franklin standing in a field, flying a kite in a thunderstorm, getting struck by lightning. That is not what happened. If lightning had actually struck his kite, he would almost certainly have been killed. What Franklin actually did in June of 1752 was much more careful and much more clever. Franklin had already proposed that lightning was electrical in nature, that it was the same phenomenon as the sparks from a Leyden jar, just vastly larger. This was a bold claim.
Lightning was considered by many to be a supernatural force, an act of God, not something you could capture in a bottle. Franklin proposed a way to test it. He flew a silk kite, not paper, silk, because it would survive rain, with a pointed wire at the top, connected by a wet hemp string to a silk ribbon he held in his hand. The silk ribbon was the insulator. At the junction of the string and the ribbon, he tied a metal key. The idea was that if the storm clouds were electrified, charge would travel down the wet string to the key. And that is what happened. He noticed the loose fibers of the hemp string standing erect, repelling each other, a sure sign of charge. He touched his knuckle to the key and got a spark. He then charged a Leyden jar from the key, proving that the electricity from the sky behaved identically to the electricity from his laboratory generators. Lightning was electricity.
The same stuff that made amber attract feathers, that jolted poor Cuneus through his Leyden jar, was the same force that split trees and set buildings ablaze during storms. And Franklin immediately turned this knowledge into something practical. He invented the lightning rod, a simple, pointed metal conductor mounted on a roof, connected by a wire to the ground. The rod would give lightning a safe path, protecting the building. Within a few years, lightning rods were being installed on churches across Europe. Churches that had been devastated by lightning fires for centuries because of their tall steeples. Some clergy initially objected, arguing that deflecting God's lightning was interfering with divine will. But pragmatism won out quickly once the church next door stopped burning down. Now, I want to pause here and notice something. We have travelled a long way from lodestones and amber.
We have gone from ancient curiosities to a world where people can store electricity in jars, pull it from the sky, and use it to protect buildings. But through all of this, through the Leyden jars and the kites and the sparking machines, one question has been hovering in the background, unasked and unanswered. What is actually in the gap? When a charged Leyden jar reaches out and shocks someone's finger, what is happening in the space between the jar and the finger in the instant before the spark jumps? When lightning rips through the sky, what is the structure of the space between the cloud and the ground? When a lodestone pulls iron toward it, what is filling the emptiness between them? Nobody was asking these questions yet. Not really. People were focused on what electricity and magnetism did, not on how they did it. They were mapping the behavior of forces without wondering about the medium through which those forces acted.
But that question, the question of what fills the gap, was about to become unavoidable. Because the next chapter of this story involves a dead frog, two feuding Italian professors, and a device that would give scientists something they had never had before: a steady, continuous flow of electric current. And that steady flow would make it possible to discover the deepest connection in all of physics. The connection that would finally tear down the wall between electricity and magnetism and reveal them as two faces of the same invisible presence filling every inch of space around you. In 1780, in the Italian city of Bologna, a professor of anatomy named Luigi Galvani was dissecting frogs. Frogs were the standard experimental animal for anatomists in that era, cheap, available, and their legs would twitch visibly when you stimulated the nerves, making them useful for studying how the body worked. And Galvani noticed something strange. When a metal scalpel touched the leg of a dead frog near an electrostatic machine that happened to be sparking nearby, the leg twitched violently, as if the frog were momentarily alive. Galvani was fascinated. He spent years investigating, trying different metals, different configurations. He found that he could make frog legs twitch by touching them with two different metals at the same time, say a copper hook and an iron plate. No electrostatic machine needed, just the two metals and the frog tissue. Galvani concluded that the electricity was coming from the frog itself. He called it animal electricity, and he believed he had discovered an inherent electrical force in living tissue. It was a reasonable interpretation. The electric torpedo fish had been known since Roman times, proof that animals could produce electricity. Maybe all animal tissue had this property. But another Italian professor, a physicist at the University of Pavia named Alessandro Volta, disagreed. Volta believed the frog was just a detector, a very sensitive one, but a detector nonetheless. The real source of the electricity, he argued, was the contact between the two different metals. The frog's leg was the instrument, not the generator. And so began one of the great scientific arguments of the 18th century. Galvani and Volta went back and forth, publishing papers, conducting experiments, each absolutely convinced the other was wrong. Volta eventually built something extraordinary to prove his point. A device that could produce electricity from metals alone, no frog required. He took small discs of copper and small discs of zinc, each about the size of a coin, and stacked them in a vertical column. Copper, zinc, then a piece of cardboard soaked in brine, then copper, zinc, another wet disc, and so on, alternating all the way up. Just a neat little tower of metal and wet cardboard. And when you touched a wire to the bottom disc and another wire to the top disc, you got a continuous flow of electric current. Not a spark, not a single jolt, but a steady, persistent stream of charge flowing through the wire, as long as the chemical reactions inside the pile kept going. He announced it in a letter to the Royal Society in London, dated March 20th, 1800, the first day of a new century. And the device, the voltaic pile, was the first true battery. Think about what Volta had just given the world. For the entire history of electrical experimentation, going back to those friction machines and Leyden jars, people had only ever had access to static electricity. Brief, violent, hard to control. You charged something up, discharged it in a single crack, and then you had to start over. It was like trying to study water by throwing individual cups of it against a wall. But now, suddenly, here was a faucet, a source you could turn on and leave running. You could pass a current through a wire for minutes, for hours. You could study what happened when electricity flowed continuously, not just in sudden bursts. And that changed absolutely everything about what was possible. And what changed first was chemistry. Because steady current let you do something that no single spark from a Leyden jar could ever do. You could sustain a continuous electrochemical reaction. Within 6 weeks of Volta's announcement, Nicholson and Carlisle had split water into hydrogen and oxygen. Think about what that means. Water, the most familiar substance on Earth, the stuff you drink and bathe in and watch fall from the sky, turned out to be made of two invisible gases, and the force holding those gases together in the water molecule could be broken by the steady push of an electric current. This was not just a chemistry result, it was an insight into the nature of matter itself. It suggested that the forces holding atoms together in molecules, the forces that make chemistry work, might be electrical in nature. And that turned out to be exactly right. The chemical bond, the thing that holds water together, the thing that holds your DNA together, the thing that makes every material in the world what it is an electromagnetic phenomenon. The electrons shared or transferred between atoms when they form bonds are held by the electromagnetic force. Chemistry is applied electromagnetism. Humphrey Davy grasped this connection with an almost predatory enthusiasm. He was not content to just split water. He wanted to split everything. He built batteries of ever-increasing size. His largest, installed at the Royal Institution, had over 2,000 pairs of plates, and he used that battery to tear apart substances that had resisted every other method of decomposition. Alkali metals, alkaline earth metals, elements that were so reactive they never existed in pure form in nature. All of them yielded to the relentless push of electrical current. The discovery of potassium in 1807 was particularly dramatic. Davy passed current through a piece of moistened caustic potash, and tiny globules of silvery metal began forming at one electrode. Some of them immediately burst into flame upon contact with the air, burning with a brilliant violet flash. Potassium was so ferociously reactive that it could not exist in the open atmosphere for more than a moment before combining with moisture or oxygen. But there it was, pulled from its hiding place by electricity, a pure element that no human eye had ever seen before. Davy's laboratory assistant, the one who watched him dance around the room that day, was a young man named Michael Faraday.
Faraday had been working at the Royal Institution for about 5 years at that point, hired as a general assistant, cleaning equipment, preparing demonstrations, helping Davy with experiments. He was learning, absorbing, watching, and the seeds of everything he would later accomplish were being planted in those early years, in that laboratory, watching Davy use electricity to unlock the secrets of matter. Within weeks of Volta's letter reaching London, researchers across Europe were building their own piles and making discoveries that would have been completely impossible with static electricity. William Nicholson and Anthony Carlyle stuck the wires from a voltaic pile into a container of water and watched it bubble. Gas was forming at both wire tips, at one end hydrogen, at the other oxygen. They had split water into its component elements using electricity. This was electrolysis, the first clear proof that electricity and chemistry were deeply connected.
Humphrey Davy, a brilliant young chemist at the Royal Institution in London, took electrolysis and ran with it. He built enormous voltaic piles and used them to decompose substances that no other method had ever been able to break apart. In 1807, he passed current through moistened caustic potash and watched tiny globules of a shiny silvery metal appear at one of the electrodes. Some of them burst into flame on contact with air. He had just discovered potassium, an element nobody had ever seen in pure form. His assistant later reported that Davy was so excited he literally danced around the laboratory. Within days, he had isolated sodium the same way, then barium, then strontium, then calcium, element after element, pulled from compounds that had resisted every other method. Electricity was no longer a curiosity. It was a tool that could crack open the fundamental structure of matter. But here is what I want you to notice. Through all of this, through the batteries and the electrolysis and the dancing chemists, nobody was thinking about the gap. Nobody was asking what was happening in the space around the wire, or between the electrodes, or in the invisible region surrounding a current. They were focused on what electricity did, the effects it produced, the reactions it triggered. The space between things was still just empty space, a void through which forces somehow teleported. And then, on an April afternoon in 1820, in a lecture hall at the University of Copenhagen, a Danish professor named Hans Christian Ørsted was about to change all of that. He was about to discover something that would crack the wall between electricity and magnetism wide open. And he was about to do it almost by accident. Ørsted had actually been thinking about a possible link between electricity and magnetism for years. He was influenced by the German Romantic tradition in philosophy,
which held that all the forces of nature were fundamentally unified, that electricity, magnetism, heat, light, and chemical action were all expressions of some deeper single force. It was a beautiful idea, and in some ways remarkably prescient, but it was considered a bit mystical by most serious physicists who thought electricity and magnetism were completely separate phenomena. Gilbert had said so 2 centuries earlier, and nothing since had contradicted him. But Ørsted kept wondering, and in April of 1820, during a lecture demonstration for his students, he noticed something strange. He was showing them how a wire heats up when you pass electric current through it, a standard demonstration using a voltaic pile, and he had a compass sitting on the table nearby. When he connected the wire to the battery and current started flowing, the compass needle moved.
It swung away from north and pointed in a different direction. Now, there is some debate among historians about how accidental this discovery really was. Some accounts portray it as pure serendipity, a chance observation during a routine lecture. Others suggest Ørsted had been deliberately looking for a connection between electricity and magnetism for years, influenced by his philosophical convictions, and that this demonstration was a carefully planned test. The truth is probably somewhere in between. Ørsted had been trying various configurations for a while and getting ambiguous or negative results. But on that particular day, with a strong enough current from a good battery and a sensitive compass placed in just the right position, the effect was unmistakable. And here is what makes the geometry of the discovery so important, so disorienting for anyone trained in the physics of that era.
Every force they had ever studied, gravity, electrical attraction, the pull of a rope, the push of a hand, acted in straight lines between 2 objects. You push, the thing moves in the direction you push. Gravity pulls straight down. Charged objects attract or repel along the line connecting them. Forces acted along the axis connecting the source of the force to the thing being acted upon. But this magnetic force produced by the current, it did not act along any line connecting the wire to the compass. It acted at right angles. It circled the wire. The compass needle did not point toward the wire or away from it. It pointed around it. This was something geometrically new, something nobody had a framework for, something that did not fit into any existing category of force. Ørsted spent months mapping the effect with painstaking care. He tried different wire orientations. He placed the compass above the wire, below the wire, to the left, to the right. He reversed the current and watched the needle swing the other way. He moved the compass further from the wire and watched the deflection decrease. Everything he found was consistent. The magnetic effect circled the wire in a definite pattern, and the direction of that circular pattern depended on the direction the current was flowing. He published his results in a 4-page Latin pamphlet in July of 1820 and mailed copies to every major scientific society in Europe. And the response was immediate and intense, because the implications were enormous. Gilbert's 200-year-old wall between electricity and magnetism had just been breached. The 2 forces, which everyone had treated as completely separate since 1600, were connected. An electric current could produce a magnetic effect. The universe was more deeply interconnected than anyone had suspected. Now, here is what made this observation so deeply weird. The needle did not point toward the wire, the way you might expect if the wire were simply pulling on it. And it did not point away from the wire, the way you would expect if it were pushing. The needle swung sideways, perpendicular to the wire. That was bizarre. Nothing in anyone's understanding of either electricity or magnetism predicted a force that acted at right angles. Gravity pulls things straight toward the center of the Earth. Electric charges attract or repel along the line connecting them. Every force anyone had ever studied acted in straight lines, either toward or away. But this new force, this magnetic effect created by an electric current, it wrapped around the wire. It circled it, like invisible rings slipped around a finger. Ørsted spent the next several months experimenting carefully, confirming the effect, mapping its geometry. If you reversed the current, the needle swung the other way. If you moved the compass above the wire instead of below it, the deflection reversed. The magnetic effect formed a circular pattern around the wire, and the direction of that pattern depended on the direction the current was flowing. He published his results in July of 1820 in a short Latin pamphlet that he sent to scientific societies across Europe. And the effect was immediate. This was an earthquake. Think about what Ørsted had shown. A moving electric charge, because that is what a current is, charges flowing through a wire, creates a magnetic field around it. Not an electric field, a magnetic field. The kind of field that moves compass needles, the kind that lodestones have. Electricity, when it moves, produces magnetism. Gilbert's careful distinction between the two forces was correct as far as it went. Static electricity and static magnetism do behave differently. But it missed something profound. When charges move, when electricity flows, something new happens, something magnetic. The wall between the two forces had a crack in it, and that crack was about to become a canyon. The news reached Paris within weeks, and a French physicist named André-Marie Ampère basically lost his mind with excitement. Ampère was brilliant, intense, and had lived a life marked by tragedy. His father was guillotined during the French Revolution when André-Marie was just 18. The trauma shaped him deeply. He threw himself into science with a kind of desperate, driven focus. And when he heard about Ørsted's discovery in September of 1820, he became consumed by it. Within a single week, 1 week, Ampère had worked out the first mathematical description of the force between two current-carrying wires. And what he found was genuinely beautiful. If you run current through two parallel wires in the same direction, the wires attract each other. If you run the currents in opposite directions, they repel. Two wires, no magnets anywhere, just flowing electricity. And yet they push and pull on each other as if they were magnets. Ampère realized something staggering. He proposed that magnetism itself, all magnetism, the magnetism of lodestones, of compass needles, of the Earth, might be nothing more than the result of tiny electric currents circulating inside matter. Inside every magnet, he suggested, there are countless little loops of current, all spinning in the same direction, and their combined effect is what we experience as magnetism. Let that sit for a moment. Every magnet you have ever held, every compass needle that has ever pointed north, every magnetic latch on a cabinet door, all of it might come from electric charges in motion. Not from some separate, mysterious, magnetic substance, but from electricity. Moving electricity. Ampère did not have the tools to explain what those tiny currents actually were. That would require understanding atoms and electrons, which would not come for another 70 or 80 years. But the core idea was right. And it is one of those insights that, once you hear it, changes how you see everything. The next time you stick a magnet to your refrigerator, you are watching the collective effect of trillions upon trillions of tiny current loops inside that magnet, all spinning in roughly the same direction, all creating their own miniature magnetic fields that add up into something strong enough
to hold a piece of paper against a steel door. Within months of Ørsted's announcement, other researchers pushed the connection further. A French instrument maker named François Arago showed that you could magnetize an iron needle by wrapping it in a coil of current-carrying wire.
And an English experimenter named William Sturgeon took that idea further in 1825, bending a piece of iron into a horseshoe shape, wrapping it with wire, and passing current through the coil. When the current was on, the iron became a powerful magnet, strong enough to lift objects many times its own weight. When the current was off, the magnetism disappeared. Sturgeon had invented the electromagnet. This was enormous. Controllable magnetism. You could turn it on, turn it off, make it stronger or weaker by adjusting the current. And controllable magnetism would eventually become the beating heart of nearly every electrical machine that followed: motors, generators, telegraphs, relays, hard drives. But the biggest question was still hanging in the air, unanswered. Ørsted had shown that electricity can create magnetism. Could you reverse it? Could magnetism create electricity?
If moving charges produce a magnetic field, could a magnetic field somehow produce moving charges? Could you run the process backward? That question would consume the next decade of research, and the person who finally answered it, who cracked it after 10 years of trying, who would then go on to fundamentally reshape how we think about forces and fields and the nature of empty space, was a man with almost no formal education, a man who could not do advanced mathematics, a man who had been apprenticed to a bookbinder at the age of 13 and had taught himself science by reading the books that came through the shop. His name was Michael Faraday. And what he saw, what he understood about the invisible something hiding in the gap between a magnet and a piece of iron, would change the course of physics forever. Michael Faraday was born in 1791 in Newington Butts, a neighbourhood in South London.
His father was a blacksmith who had moved the family down from the north of England. The family was poor. Faraday had almost no formal schooling. At 13, he was apprenticed to a local bookbinder, a man named George Rebow, and for the next 7 years he learned to bind books and sell stationery. But Faraday read the books that came through the shop. He read them voraciously, especially the science books. An encyclopedia entry on electricity caught his attention. A popular book on chemistry lit a fire in him. He started performing simple experiments in the back of the shop, building crude batteries from copper coins and zinc discs, reproducing the electrolysis experiments he had read about. And then, in 1812, a customer gave him tickets to a series of public lectures at the Royal Institution, given by the famous chemist Humphrey Davy, the same Davy who had danced around his lab after discovering potassium. Faraday attended the lectures and took meticulous notes, writing down every demonstration, every explanation, every line of reasoning. Then he bound those notes into a beautiful volume, because he was a bookbinder after all, and sent them to Davy as a kind of job application. Davy was impressed enough to hire him as a laboratory assistant in 1813, and from that position, with no university degree, no mathematical training to speak of, Michael Faraday would go on to make discoveries that rival anything Newton or Einstein ever accomplished. He became, by the end of his career, one of the greatest experimental scientists who ever lived. And his greatest contribution was not a specific discovery, though he made many. It was a way of seeing, a way of thinking about what fills the space between things, a picture of the invisible. Now, most people, when they think of Faraday, think of electromagnetic induction, the discovery that a changing magnetic field creates an electric current. And that is certainly his most consequential discovery in practical terms. But I would argue that Faraday's deepest contribution was not any single experiment. It was a way of thinking, a picture of reality. And that picture centered on something he called the field. To understand why this was so radical, you have to understand how physicists in the early 19th century thought about forces. The dominant framework, the one established by Newton and refined by Laplace, Coulomb, Poisson, and others, was action at a distance. The idea was simple. Two objects exert a force on each other across the space between them, and that force depends on the distance and the properties of the objects. The force acts instantaneously. It does not travel. It is not mediated by anything. The two objects just know about each other somehow across the gap. This framework was mathematically elegant. Coulomb's law for electric charges, which says the force between two charges is proportional to the product of the charges divided by the square of the distance between them, was a beautiful, precise, quantitative description. You could calculate the force to as many decimal places as you wanted. The formula worked. It made predictions that matched experiments perfectly. But notice what the formula does not tell you. It does not tell you what is happening in the space between the charges. It describes the force as if it teleports from one charge to the other. The space between them is irrelevant, just empty void. The formula treats the charges as the only things that matter, and the space between them as nothing. Faraday looked at this and felt that something was wrong. Or perhaps not wrong exactly, but incomplete. He kept coming back to the space between things when he sprinkled iron filings around a magnet and saw those beautiful curves arcing from pole to pole. He did not see a pattern imposed on passive particles by a force reaching out from the magnet. He saw something that was already there in the space. The filings were revealing it, not creating it. The curves existed before the filings arrived. The filings were just making the invisible visible. He called these curves lines of force, and he believed they were real. Not real in the way a table is real, something you can knock on and feel its solidity, but real in the way a breeze is real, an influence you can detect and measure even though you cannot see it. The lines of force, in Faraday's view, were threads of influence extending through space, carrying the magnetic force from the magnet to whatever the magnet was acting on. And the force was not acting at a distance, it was acting locally, transmitted step by step along these lines, like a wave traveling down a rope. Each point in space was influenced by its immediate neighbors, and the force propagated through the field from one point to the next. This was a profoundly different picture from action at a distance. In the old picture, the important things were the charges and magnets, and the space between them was empty. In Faraday's picture, the important thing was the space itself, the field filling that space, and the charges and magnets were just sources and sinks of the field, the places where it originated and terminated. Think about what that means for our question about the gap. In the old picture, the gap between a magnet and a piece of iron is empty, nothing there, and the force somehow jumps across it. In Faraday's picture, the gap is full of the field, full of lines of force, full of a real physical presence that carries the force from one object to another. Faraday also realized something crucial about the field that nobody else had articulated clearly. The field stores energy. Think about a bar magnet and a piece of iron. When they are far apart, they barely interact. When they are close together, the pull is strong. Where does the energy go when you pull the iron away from the magnet against that pull? You are doing work, applying a force over a distance. That energy has to go somewhere. In the action at a distance picture, it is hard to say where the energy is. It is stored in the interaction, somehow, in a delocalized way. But Faraday thought the energy was in the field, literally in the space around the magnet. When you bring the iron close, the field between them becomes stronger, more concentrated, and the energy stored in that region of the field decreases as it pulls the iron in. When you pull the iron away, you are putting energy back into the field, stretching it, straining it, and that energy is stored right there, in the gap, in the lines of force. This turned out to be exactly right. Maxwell would later show that the energy density of the electromagnetic field, the amount of energy per unit volume stored in the field at any point in space, is proportional to the square of the field strength at that point. The field literally contains energy, and that energy is physically located in the space where the field exists. The gap between the magnet and the iron is not empty. It is full of energy stored in the field. But let us start with the discovery, because the discovery came first, and it took him 10 years to get there. Faraday heard about Ørsted's and Ampere's work almost immediately. He was working at the Royal Institution, surrounded by the best scientists in England, and the news from Denmark and France electrified the scientific community. Ørsted had shown that a current creates a magnetic field around the wire. The field circled the wire. And Faraday, in 1821, demonstrated this beautifully by building a device that was, in essence, the first electric motor. He suspended a wire so that one end dipped into a cup of mercury, with a permanent magnet standing upright in the center. When he passed current through the wire began to rotate continuously around the magnet, driven by that circular magnetic force Ørsted had discovered. It was crude, just a wire circling a magnet in a cup of mercury. But the principle was profound. He had converted electrical energy into continuous mechanical motion. Every electric motor in the world, every fan, every washing machine, every electric car, traces back to Faraday's mercury cup in 1821. But the bigger question haunted him. If electricity could create magnetism, could magnetism create electricity? Could you reverse the process? He tried for a decade. He placed magnets near wires connected to galvanometers, sensitive devices that could detect tiny electric currents. He arranged the strongest magnets he could find, set up wires near them in every configuration he could imagine, and watched the galvanometer for any flicker of a response. Nothing. The galvanometer needle sat there, motionless, year after year. And here is the thing that makes this story so deeply human. The reason Faraday kept failing was not that the effect did not exist. It was that he was looking for the wrong thing. He was looking for a steady current produced by a stationary magnet. He would place a magnet next to a wire, watch the galvanometer, and see nothing. What he did not realize, what nobody realized, was that you need change. You need motion or variation. A stationary magnet sitting next to a stationary wire produces absolutely nothing. But move the magnet or change the magnetic field in some way, and suddenly current flows. He finally cracked it on August 29th, 1831. He had wound 2 separate coils of wire around an iron ring, like a donut wrapped with wire on both sides. One coil was connected to a battery, the other to a galvanometer. When he connected the battery, sending current through the first coil and creating a magnetic field in the iron ring, the galvanometer on the second coil kicked. Just for an instant, a brief pulse of current, then it settled back to 0. When he disconnected the battery, the galvanometer kicked again, this time in the opposite direction, then back to 0. Only during the change, only during the moment when the magnetic field was increasing or decreasing. A steady magnetic field produced nothing. A changing magnetic field produced electricity. This is electromagnetic induction. And it is, without exaggeration, one of the most important discoveries in the history of human civilization. Because here is what it means in practical terms. Every power plant on Earth,
coal, gas, nuclear, hydroelectric, wind, generates electricity by spinning magnets near coils of wire. That is the fundamental mechanism. You change a magnetic field near a conductor, and current flows. Faraday figured this out with an iron ring and some wire in a basement laboratory in London, and it powers the modern world. Within weeks, he had built a simpler version, a copper disc spinning between the poles of a magnet, producing a continuous current. The first true electric generator. He called it a new electrical machine. It was about the size of a dinner plate. Today, the generators at a large power station can weigh hundreds of tons and produce enough electricity for 1 million homes. But the principle is identical. Now, most people, if they had just made one of the most important discoveries in the history of science, might take a moment to celebrate. And Faraday did continue developing practical applications of induction. But something else was occupying his mind. Something that went deeper than any individual experiment. Something that the other physicists of his era were not seeing or were not willing to see. Faraday was thinking about the gap. When he sprinkled iron filings on a piece of paper held over a magnet and watched the filings arrange themselves into those beautiful curving lines arcing from one pole to the other, he did not see a cute pattern. He saw something real. He believed those curves represented actual, physical structures existing in the space around the magnet. He called them lines of force, and he was convinced they were not just a useful illustration, not a mathematical convenience, not a way of visualizing what was happening. He believed they were the thing itself, the mechanism, the invisible architecture through which the magnetic force was transmitted. Think about what this means.
For everyone else, the magnet exerted a force on the iron through some kind of instantaneous, mysterious action at a distance. The magnet was here, the iron was there, and somehow, across the gap of empty space between them, a force reached from one to the other. How? Nobody knew. It just happened. Newton himself, when asked how gravity could act across empty space, had famously said, "I frame no hypotheses." He could describe the force mathematically with exquisite precision, but he refused to speculate on the mechanism. Faraday said no. He said the force is not acting at a distance. The force is local. The magnet creates something in the space around it, and that something, those lines of force, is what acts on the iron. The iron does not feel the magnet. The iron feels the field. The magnet creates the field fills the space, and the field pushes the iron. The force is not teleporting across empty space, it is being transmitted through a medium, an invisible, intangible, but very real medium that permeates the gap between the magnet and anything it attracts. Faraday called this medium a field. And that word, that concept, would turn out to be one of the most revolutionary ideas in the entire history of physics. But here is the problem. Faraday could not express any of this in mathematics. He thought in pictures, in physical intuitions, in tangible images. He could describe what he saw with extraordinary clarity and precision. He could design experiments of dazzling elegance. But the mathematical formalism that the other physicists demanded, the equations, the proofs, the quantitative predictions, those were beyond his training. And in the culture of 19th century physics, if you could not write it in equations, it was considered vague, qualitative, not quite serious.
Most of the mathematical physicists of the day dismissed Faraday's lines of force as a charming metaphor, useful for a man who could not do calculus, but not rigorous science. The established framework was action at a distance, forces reaching instantaneously through empty space, and it worked beautifully as a mathematical description? Why replace it with some vague notion of invisible lines filling space? But there was one young man who read Faraday's papers and saw something extraordinary in them. One person who had both the physical intuition to appreciate what Faraday was saying and the mathematical power to translate it into the language the rest of physics demanded. And what he would do with Faraday's vision would change the course of science forever. His name was James Clerk Maxwell. And the story of what he did deserves to be told slowly, because it is one of the most beautiful intellectual achievements in human history. Maxwell was born in Edinburgh on June 13th, 1831, the same year Faraday discovered electromagnetic induction. He grew up on a country estate in southwestern Scotland called Glenlair, surrounded by rolling hills and farmland. And from a very young age, he was relentlessly, almost alarmingly curious. His childhood nickname was Dafty, which gives you a sense of how his constant questioning struck the other children. He wanted to know how everything worked. "What's the go of that?" he would ask, over and over, about anything and everything. What is the go of it? What makes it do what it does? And if you gave him an answer, he would follow up with, "But what's the particular go of it?" He wanted the deeper mechanism, always. By the time Maxwell arrived at Cambridge in the early 1850s, he was already an extraordinary mathematician. He had published his first scientific paper at 14, a method for drawing certain mathematical curves using a piece of string and some pins. 14 years old. But what made Maxwell truly remarkable was not raw mathematical ability alone. Plenty of people at Cambridge could handle equations. What set Maxwell apart was a rare combination. He could think in pictures and in equations at the same time. He could hold a physical intuition in one hand and a mathematical structure in the other, and see how they mapped onto each other. And that was exactly the skill needed to take Faraday's field concept and turn it into something the rest of physics would have to take seriously. Maxwell read Faraday's experimental researches in electricity, all 3 volumes, thousands of paragraphs of meticulous experimental description. And where other mathematicians saw vague hand-waving about lines of force, Maxwell saw the skeleton of a profound mathematical theory waiting to be fleshed out. He said later that he deliberately set out to translate Faraday's ideas into mathematical form, not to replace them, but to show that Faraday's physical intuitions were not just qualitatively interesting, they were quantitatively exact. Maxwell started by imagining the magnetic field as something like a fluid flowing through space. He did not think it literally was a fluid. He used the mathematics of fluid flow, the equations that describe how liquids move through pipes, how pressure gradients drive currents of water, as an analogy, a scaffolding, to build equations describing how the field behaved. This was a technique he was brilliant at. Using one physical system you already understand as a mathematical model for another system you are trying to figure out. His first paper on the subject, published in 1855 and called On Faraday's Lines of Force, was essentially a translation job. He showed that Faraday's lines of force could be described by precise mathematical expressions, and that those expressions obeyed specific rules. The field was not vague at all. It had structure, it had geometry, it followed laws. But Maxwell was not done. Over the next decade, he kept pushing deeper. He developed increasingly sophisticated mathematical descriptions of how electric and magnetic fields behaved, how they were created by charges and currents, how they interacted with each other. Maxwell's approach was methodical and creative in equal measure. He started with what was known. There were 4 fundamental experimental facts about electric and magnetic fields, each associated with a specific scientist's name, and each describing a specific aspect of how the fields behave. The first fact was Gauss's law for electricity, which says that electric charges are the sources of electric fields. Positive charges are like fountains, where electric field lines originate, and negative charges are like drains, where field lines terminate. If you draw an imaginary closed surface around a positive charge, more field lines are coming out of the surface than going in. The total outward flow of field through the surface is proportional to the amount of charge inside. No charge inside, no net flow. Positive charge inside, net flow outward. Negative charge inside, net flow inward. The second fact was Gauss's law for magnetism, which says that magnetic field lines do not have sources or sinks. They do not start anywhere, and they do not end anywhere. Every magnetic field line is a closed loop. This means there are no magnetic charges, no North Pole particles or South Pole particles floating around on their own. Every magnet has both a north and a south pole. You cannot cut a magnet in half and get a separate north and a separate south. You just get 2 smaller magnets, each with its own north and south. Gilbert had suspected this centuries earlier. Gauss's law for magnetism formalized it. The third fact was Faraday's law of induction, which says that a changing magnetic field creates an electric field. More precisely, if the magnetic field passing through a loop of wire is changing in time, an electric field is created that circulates around the loop, driving a current. This was Faraday's great discovery of 1831, now expressed as a precise mathematical relationship. And the fourth fact was Ampere's law, which says that an electric current creates a magnetic field that circles around the current. This was Ørsted's and Ampere's discovery from 1820, also expressed mathematically. 4 facts, 4 equations, each one describing a piece of how electric and magnetic fields are created and how they behave.
And Maxwell's genius was to look at these 4 equations together and notice that something was not quite right. There was an inconsistency. The equations, as they stood, contradicted one of the deepest principles of physics: conservation of charge. The principle that electric charge can never be created or destroyed. Here is where it gets technical, but I want you to follow it because the reasoning is beautiful. Ampere's law says that a circulating magnetic field is produced by an electric current flowing through the loop around which the field circulates. But what if the current is not steady? What if, instead of a continuous wire carrying a steady current, you have a capacitor? 2 metal plates separated by a gap. Current flows into one plate, charge builds up on it, and an electric field grows between the plates. Eventually, the current flows out of the other plate.
From the outside, it looks like current is flowing through the gap between the plates, even though no actual charge crosses the gap. The current goes in one side, comes out the other, and in between, what happens? Ampere's law, as originally written, cannot handle this situation. It says the magnetic field around a loop depends on the current passing through the loop. But if the loop goes between the capacitor plates, no current crosses it, and yet the magnetic field is clearly there. Because further along the circuit, where the wire carries current, the field exists. Maxwell realized that the changing electric field between the capacitor plates acts like a current in its ability to produce a magnetic field. He called it the displacement current, and he added it to Ampere's law, modifying the equation to say that a circulating magnetic field is produced either by an actual current or by a changing electric field. Either one works. Both generate a magnetic field around them. This might seem like a small, technical fix, just patching an equation to handle a special case, but the consequences were anything but small. Because the displacement current meant that a changing electric field, even in totally empty space, with no wires, no charges, nothing at all, could create a magnetic field. And that changed everything. And then he found something that nobody expected. He found that a changing electric field should produce a magnetic field. Now, Faraday had already shown the reverse. A changing magnetic field produces an electric field. That was electromagnetic induction. But Maxwell's equations were telling him something new. The relationship went both ways. If a magnetic field changes in time, it creates an electric field. And if an electric field changes in time, it creates a magnetic field. This was a purely theoretical prediction. Nobody had observed it directly. There was no experimental evidence for it. But the mathematics demanded it. There was a gap in the equations, an inconsistency that only disappeared if you added this extra term, this displacement current, this idea that a changing electric field is, in some sense, equivalent to a flowing current in its ability to generate a magnetic field. Maxwell trusted the mathematics. He added the term, and the moment he did, something astonishing fell out of the equations. When he combined all the relationships together, the ones describing how electric fields are created by charges, how magnetic fields are created by currents, how a changing magnetic field creates an electric field, and now how a changing electric field creates a magnetic field, he found that the equations predicted waves. Self-sustaining, self-propagating waves of intertwined electric and magnetic fields rippling through space. Here is how it works, and this is worth slowing down for, because it is one of the most beautiful mechanisms in all of physics.
Imagine a region of space where an electric field is changing. Maybe a charge is oscillating back and forth. That changing electric field creates a magnetic field around it. But that magnetic field is also changing, because the electric field that created it is changing. And a changing magnetic field creates an electric field, which is also changing, which creates a magnetic field, which is changing, which creates an electric field. You see what is happening. The two fields are leapfrogging through space, each one creating the other, sustaining each other, carrying each other forward in a self-perpetuating ripple that needs no wire, no medium, no material substance to travel through. Just empty space, filled with the two fields, endlessly regenerating each other as they race outward. An electromagnetic wave. And Maxwell calculated the speed of these waves.
He plugged in the known constants, the measured strength of electric forces and the measured strength of magnetic forces, numbers that had been carefully determined in laboratories. And he got a speed. About 193,000 miles per second. And the measured speed of light at the time was about 195,000 miles per second. Maxwell did the calculation in the early 1860s, and the result left him stunned. The speed of his predicted electromagnetic waves depended on only two numbers, two constants that had been measured independently in electrostatics and magnetostatics laboratories. One constant described the strength of the electric force between charges. The other described the strength of the magnetic force between currents. Neither constant had anything obvious to do with light. They were just properties of electric and magnetic interactions, measured with Leyden jars and galvanometers and torsion balances.
And yet, when Maxwell combined them in the specific way his equations demanded, out came a number that was, within the precision of the measurements, identical to the speed of light. Let me say that again, because I think the significance sometimes gets lost. Two numbers, measured in completely separate electrical experiments, by completely separate people, using completely separate equipment, having nothing to do with light or optics, produce, when combined according to the rules of electromagnetic theory, the speed of light. The odds of that being a coincidence are essentially zero. It is as if you measured the height and width of two different buildings on two different continents and discovered that multiplying them gave you the exact distance from the Earth to the Moon. The numbers have no obvious connection, and yet they produce a result that matches a known physical quantity with eerie precision. Maxwell knew immediately what this meant. The speed was not a coincidence.
Light is electromagnetic. Light is a wave of the electromagnetic field. The field that makes magnets work, and the field that makes rubbed amber attract straw, and the field that carries light from the sun to the earth are the same field. One field, one set of equations, one invisible architecture underlying everything. He presented this result in a lecture to the Royal Society of London in 1864 and published the full theory the following year. The paper, A Dynamical Theory of the Electromagnetic Field, is dense, mathematical, and not easy to read, even for trained physicists. But its conclusions are among the most far-reaching in the history of science. The numbers were not just close, they were practically identical. And Maxwell wrote, in that understated way Victorian scientists had, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena."
Think about what he was saying. Really stop and think about it for a moment. Light, the thing you see with, the thing that comes from the sun, the thing that bounces off every object around you and enters your eyes and lets you perceive the world. Light is an electromagnetic wave. It is a ripple in the same fields that make magnets stick to refrigerators and compass needles point north. The same force that made lodestones attract iron in ancient Magnesia is the same force that lets you see. Electricity, magnetism, and light. Three phenomena that seemed completely unrelated for the entire history of civilization are all different expressions of a single, deeper thing. Maxwell unified them. He showed that they are all aspects of the electromagnetic field, that invisible something filling every inch of space. The thing Faraday had glimpsed in his iron filing patterns. The thing that was always there in the gap between the magnet and the iron.
And he captured the whole thing in 4 equations. Just 4.
Today we call them Maxwell's equations. They are, in the opinion of many physicists, the most beautiful and consequential equations in all of science. 4 compact mathematical statements that describe every electromagnetic phenomenon in the universe. Every radio wave, every X-ray, every beam of light, every magnetic field around every wire, every spark, every aurora, every signal from every cell tower, every pulse of energy from every star. All of it flows from those 4 lines. But here is the thing. When Maxwell published his work, in its mature form in his 1865 paper, A Dynamical Theory of the Electromagnetic Field, the world did not immediately stand up and applaud. The reception was mixed. The mathematical formalism was dense. Maxwell's original presentation used quaternions, a mathematical notation that most physicists found clunky and hard to follow.
And the physical predictions, as extraordinary as they were, had a problem. Nobody had ever detected these electromagnetic waves. Light was already known to be a wave, sure, but the idea that you could create electromagnetic waves by other means, by oscillating charges in a wire, for instance, that was still just theory. Maxwell was claiming that if you wiggled an electric charge back and forth fast enough, invisible waves of interlocked electric and magnetic fields would radiate outward from it at the speed of light. Beautiful prediction. But where was the evidence? Maxwell himself never lived to see the confirmation. He died on November 5, 1879, at the age of 48, from abdominal cancer, the same disease that had killed his mother when he was 8. He spent his last weeks at Glenlair, the estate where he had grown up, and by all accounts he faced death with the same quiet composure he had brought to everything else.
He left behind a theory that would reshape the world. But he never got to see it proven right. That job fell to a young German physicist working in a laboratory in Karlsruhe. And the story of how he did it is one of those moments in science where a theoretical prediction meets experimental reality and the universe says yes. Heinrich Hertz was born in Hamburg in 1857. He studied under Hermann von Helmholtz in Berlin and became fascinated by Maxwell's theory. And in 1887 and 1888, he set out to test Maxwell's prediction directly. Could you create electromagnetic waves in a laboratory using nothing but oscillating electric charges and detect them across a room? He built a transmitter, essentially a pair of metal rods with a small gap between them, connected to a high-voltage induction coil. When the coil was activated, sparks jumped across the gap, and the charge oscillated back and forth rapidly between the two rods.
If Maxwell was right, that oscillation should produce electromagnetic waves radiating outward. For his detector, Hertz used a simple loop of wire with its own tiny gap. If electromagnetic waves reached this loop, they should induce a tiny current, which would produce a spark across the detector's gap. A miniature spark, barely visible, but enough to confirm the wave's existence. Hertz set up his transmitter on one side of his laboratory. He placed the detector across the room. He fired the transmitter, and across the room, in the tiny gap of the detector loop, a spark appeared. Hertz did more than just detect the waves. He mapped their behavior with meticulous care. He showed that these invisible waves could be reflected. He placed a large zinc sheet on one side of his laboratory and showed that the waves bounced off it, just like light bouncing off a mirror. He demonstrated that the waves could be focused.
Using a curved metal reflector shaped like a parabolic mirror, he concentrated the waves and showed that the signal was stronger at the focal point. He showed that the waves could be refracted. He built a prism out of a material called pitch, a kind of hardened tar, and passed his electromagnetic waves through it. The waves bent, just like light bending through a glass prism. The angle of bending depended on the wavelength, exactly as Maxwell's equations predicted. He measured the speed of his waves. He set up standing wave patterns in his laboratory by reflecting the waves off a wall and looking for the nodes and antinodes, the points of maximum and minimum signal. From the spacing of those nodes and the known frequency of his oscillator, he could calculate the wavelength, and from wavelength and frequency, the speed. It matched the speed of light. Every test Hertz performed confirmed Maxwell's theory. The waves were electromagnetic. They travelled at the speed of light, and they behaved in every detectable way exactly like light, just at a much lower frequency, with wavelengths measured in feet rather than in millionths of an inch. Hertz published his results in 1888, and the impact on the physics community was profound. Maxwell's theory, which had been regarded by some as mathematically elegant but experimentally unconfirmed, was now vindicated. The electromagnetic field could produce self-sustaining waves that travelled through empty space. Faraday's intuition that the field was real, that the space between things was filled with something tangible, was no longer just a useful picture. It was confirmed physical reality. And yet Hertz himself, when asked about the practical applications of his discovery, dismissed the question. "It is of no use whatsoever," he reportedly said. "This is just an experiment that proves Maestro Maxwell was right." He saw it purely as a confirmation of a theoretical prediction, a beautiful piece of experimental physics with no practical consequences. He could not have been more wrong. Within just a few years, a young Italian inventor named Guglielmo Marconi, who had read about Hertz's experiments as a teenager, began tinkering with the idea of using electromagnetic waves to send messages without wires. By 1895, Marconi was sending signals across his family's estate in Bologna. By 1899, he sent a signal across the English Channel. And on December 12, 1901, he received a transmission that had crossed the entire Atlantic Ocean, from a station in Cornwall, England, to a receiving antenna in Newfoundland, Canada. The signal consisted of 3 short clicks, the Morse code for the letter S. That transmission opened the floodgates. Radio broadcasting began in the early 1920s. Television followed in the 1930s and 40s. Radar, developed during the Second World War, used electromagnetic waves to detect aircraft and ships at great distances. And from there, the cascade continued. Satellite communication, cellular networks, Wi-Fi, Bluetooth, GPS, all of them using electromagnetic waves, all of them transmitting information through the invisible field that fills every inch of space. All of them built on the foundation that Maxwell predicted and Hertz confirmed. And Hertz never saw any of it. He died in 1894, at the age of 36, from a form of blood vessel inflammation. He was gone before Marconi sent his first signal across a garden. The unit of frequency, the Hertz, is named in his honor. Every time you hear someone say megahertz or gigahertz, every time you look at the frequency setting on a radio dial, you are invoking the name of a man who thought his discovery was of no use whatsoever. He was detecting invisible waves that had traveled through the air from one side of the room to the other. Waves that were not light, not heat, not sound. Waves of pure electromagnetic energy, exactly as Maxwell had predicted. Hertz went further. He showed that these waves could be reflected off metal surfaces, just like light bouncing off a mirror. He showed they could be refracted, bent, when passing through a prism-shaped block of pitch, just like light bending through glass. He showed they travelled at the speed of light. He measured their wavelength and frequency. In every way he could test them, they behaved exactly as Maxwell's equations predicted. Maxwell was right. The electromagnetic field was real. It could carry waves through empty space. And those waves were the same fundamental phenomenon as light. When asked about the practical applications of his discovery, Hertz reportedly said, "It is of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right," which is one of the great underestimations in the history of science, because within a decade, an Italian inventor named Guglielmo Marconi would be using those waves to send wireless telegraph signals across the Atlantic Ocean. The entire age of radio communication was about to begin, followed by television, radar, cell phones, Wi-Fi, Bluetooth, GPS. Every wireless technology you have ever used is built on the waves that Hertz discovered in a physics laboratory, proving a mathematical prediction made by a quiet Scottish genius based on the physical intuition of a bookbinder's apprentice who could not do calculus. And at the center of it all, the thing that makes it all possible, is the field.
that invisible something filling the space between things. Now let us take a breath and think about where we have arrived. Because something really important has happened, something that goes beyond any individual discovery.
Before Faraday, before Maxwell, the standard view of forces was action at a distance. A magnet pulled iron through empty space. Two charged objects pushed or pulled each other through empty space. The space between them was just nothing, a void, a stage on which the actors performed, but which had no role in the performance. After Maxwell, the space is no longer empty. The space is the performance. The space is filled with the electromagnetic field, a real physical entity that stores energy, transmits force, and propagates waves. The field is not a metaphor, not a mathematical trick, not a useful visualization. It is as real as the magnet that creates it. In some sense, it is more real, because the field exists everywhere, permeating all of space, whether there are magnets around or not. The magnets just shape the field. The field is always there. And the energy stored in that field is real, measurable energy. This is something that comes directly from Maxwell's equations.
The energy density of an electric field is proportional to the square of the field strength. The energy density of a magnetic field is proportional to the square of its strength too. This means that the empty space between the plates of a charged capacitor actually contains energy. The empty space around a magnet actually contains energy. That energy can do work. It can push things. It can heat things. It is there, stored in the invisible architecture of the field. Faraday saw this. Faraday, without equations, without formal training, looked at the space around a magnet and said, "Something is there." And Maxwell proved him right in the most spectacular way possible, by showing that the something could detach itself from the magnet entirely and fly off through space at 186,000 miles per second, carrying energy and information across the universe. Light is that something. Radio waves are that something.
X-rays, gamma rays, microwaves, infrared, ultraviolet, all the electromagnetic spectrum, all of it is the field, rippling and oscillating, carrying energy from stars to eyes, from transmitters to receivers, from one side of the universe to the other. So here is where we stand. By the end of the 19th century, the picture seems complete. Electricity and magnetism are unified. Light is explained. The field is established as a real physical entity. Maxwell's equations describe everything, and the technology is already rolling. Electric motors, generators, power plants, light bulbs, telegraphs, telephones, radio. But the universe, as it turns out, had a few more surprises. Because Maxwell's equations, beautiful and complete as they seemed, were about to collide with problems that nobody anticipated. Problems that would force physics to rethink everything it thought it knew about light, about space, about time, and about the very nature of the field itself.
The first problem came from a question that seems almost too simple to be dangerous. Maxwell's equations said that electromagnetic waves travel at a specific speed, about 186,000 miles per second. But speed relative to what? Think about that. When you say a car is moving at 60 miles per hour, you mean relative to the ground. When you say a sound wave travels at about 760 miles per hour, you mean relative to the air it is moving through. So when Maxwell's equations say light travels at 186,000 miles per second, Relative to what? What is the reference frame? The obvious answer, the answer everyone assumed, was that there must be a medium, some invisible substance filling all of space through which light waves propagated, the way sound waves propagate through air. Physicists called this hypothetical medium the luminiferous ether. The ether. Light waves were vibrations in the ether, and the speed in Maxwell's equations was relative to the ether. But then, in 1887, the same year Hertz was detecting his waves, two American physicists named Albert Michelson and Edward Morley performed an extremely precise experiment designed to detect the Earth's motion through the ether. The idea was simple. If the Earth is moving through this invisible substance, then light should travel slightly faster in one direction than another, the way a swimmer moves faster going downstream than upstream. Michelson and Morley built an incredibly sensitive instrument, an interferometer, that could detect even tiny differences in the speed of light in two perpendicular directions. They found nothing, no difference, zero. The speed of light was the same in every direction, regardless of the Earth's motion. The ether, if it existed, was completely undetectable. The experiment was repeated many times with increasing precision.
The result was always the same. No ether wind, no variation in the speed of light. This was baffling. If light is a wave, it should need something to wave in. And if it is waving in something, that something should have a measurable effect on the speed. But it did not. The Michelson-Morley result sat there for nearly 2 decades, an uncomfortable thorn in the side of physics. Various people proposed explanations, hypotheses about the ether being dragged along by the Earth, or about objects contracting slightly in the direction of motion so as to mask the effect. But nothing quite worked. Nothing felt right. And then, a 26-year-old patent clerk in Bern, Switzerland, cut through the whole tangle. He was not working in the university laboratory. He was not a professor. Albert Einstein had completed his education at the Swiss Federal Polytechnic in Zurich and had been unable to find an academic position. So he took a job at the Swiss Federal Patent Office, evaluating applications for new inventions, most of them involving electrical devices, and did his physics in his spare time, mostly in the evenings and on weekends, thinking through problems on walks along the Aare River. The problem that bothered him most, the one that had been nagging at him since he was 16 years old, was about light and motion. When he was a teenager, Einstein had asked himself a thought experiment that sounds simple, but turned out to be profound. What would it be like to ride alongside a beam of light, traveling at the same speed as the light wave? What would you see? According to Maxwell's equations, light is a wave of oscillating electric and magnetic fields, and those fields must oscillate. A frozen, stationary electromagnetic wave is not a solution to Maxwell's equations. It cannot exist.
So if you caught up to a light beam and rode alongside it, you would see something that the laws of physics say is impossible: a stationary electromagnetic wave. Einstein realized that there were only 2 ways out of this paradox. Either Maxwell's equations were wrong, which seemed unlikely given how well they worked, or the assumption that you could catch up to a light beam was wrong. And that second option meant that the speed of light must be the same for all observers, regardless of their motion. You can never catch up to a light beam because it always moves at the same speed relative to you, no matter how fast you are going. Always, exactly 186,282 miles per second. In 1905, Einstein published a paper called On the Electrodynamics of Moving Bodies, and in it, he laid this out with crystalline clarity. Forget the ether, there is no ether. The speed of light is not relative to any medium,
It is an absolute, a built-in speed limit of the universe itself. And if you accept that the speed of light is the same for everyone, then you have to accept some very strange consequences about space and time. Moving clocks run slow. Moving objects contract in the direction of motion. Simultaneity is relative. Two events that happen at the same time for one observer might happen at different times for another. This was special relativity. And notice where it came from. It came from thinking about Maxwell's equations. It came from asking what the electromagnetic field looks like to different observers. The entire theory, with all its mind-bending consequences about time dilation and length contraction and the equivalence of mass and energy, grew out of a question about electromagnetism. The paper's title tells you exactly that. Not on the nature of time, not on the relativity of motion, on the electrodynamics of moving bodies. It came from the field.
And here is something that most people do not realize, something that connects directly to our story about the field in the gap. Special relativity revealed something profound about the relationship between electricity and magnetism. It showed that they are not merely connected, they are the same thing, seen from different perspectives. Here is what I mean. Imagine a wire carrying a steady electric current. The wire is surrounded by a magnetic field, as Ørsted discovered. Now imagine that you start running alongside the wire, matching the speed of the flowing electrons. From your perspective, the electrons are stationary, they are not moving. And a stationary charge does not produce a magnetic field. So where did the magnetic field go? It did not go anywhere. From your running frame of reference, what was a magnetic field in the original frame becomes an electric field. The force is still there. The effect on a nearby charge is the same, but the label has changed. What one observer calls magnetic, another observer, moving differently, calls electric. Electricity and magnetism are two ways of describing the same underlying reality. And this brings us to something that deserves a little more time, because it is one of the most beautiful and underappreciated ideas in all of physics. The idea that electricity and magnetism are not just connected, they are the same thing seen from different angles. Imagine you are standing beside a railroad track, and a train goes past you with a positive charge sitting on top of it. You are standing still. The charge is moving, and a moving charge is a current, and a current produces a magnetic field. So you, standing beside the track, detect a magnetic field around that moving charge. Now imagine your friend is sitting on the train, right next to the charge. From your friend's perspective, the charge is not moving, it is just sitting there. A stationary charge does not produce a magnetic field.
So your friend, sitting on the train, detects no magnetic field. You detect a magnetic field. Your friend does not. You are looking at the same charge. You are looking at the same region of space. But you see a magnetic field, and your friend does not. How is that possible? The answer is that the force your friend detects is not magnetic. It is electric. The same electromagnetic interaction that you describe as magnetic from your perspective on the ground, your friend describes as electric from the perspective of the moving train. The underlying reality, the underlying field, is the same. But how you divide it into electric and magnetic components depends on how you are moving. This is not a subtle philosophical point. It is physically real and experimentally verified. The magnetic force between two parallel wires carrying current, for instance, can be fully explained as an electric force if you switch to the reference frame of the moving electrons. From the electrons' perspective, they are not moving, so there is no magnetic force. But from the electrons' perspective, the positive ions in the wire are moving, and Lorentz contraction, one of the effects predicted by special relativity, causes the spacing of those positive charges to change slightly, creating a tiny charge imbalance that produces an electric force identical to what we call the magnetic force in the lab frame. The two forces are one. The electromagnetic field is a single entity, and whether you perceive a given aspect of it as electric or magnetic depends entirely on your motion relative to the charges that produce it. This unification was already implicit in Maxwell's equations, but it took Einstein's special relativity to make it explicit and unavoidable. The mathematical object that describes the electromagnetic field in relativity is called the electromagnetic field tensor, a 4x4 matrix that contains both the electric and magnetic field components mixed together, inseparable. When you change reference frames, the components shuffle. Electric field becomes magnetic, magnetic becomes electric. But the tensor itself, the underlying field, remains unchanged. It is frame independent. It is the true physical reality. Our separation of it into E and B is just an artifact of our perspective, our motion, our coordinate system. So the answer to the question, what is between the magnet and the iron, turns out to be even deeper than a magnetic field. The answer is the electromagnetic field, a single unified entity that can appear electric or magnetic or both, depending on who is looking and how they are moving. The lodestone in Magnesia and the rubbed amber in Athens were always doing the same thing. We just could not see it because we were standing still. The electromagnetic field. The division between them depends entirely on how you are moving relative to the charges. There is really only one field, the electromagnetic field, and whether you perceive its effects as electric or magnetic depends on your frame of reference. This is stunning when you really absorb it. The lodestone that attracted iron in ancient Magnesia and the rubbed amber that attracted straw in ancient Greece were doing the same thing. The force reaching through the gap, the invisible tug between magnet and iron, between charged amber and straw, is one and the same force. It just looks different depending on whether the charges involved are moving or stationary relative to you. The field in the gap is the electromagnetic field, and it does not care about our labels. But Einstein's 1905 paper contained another surprise, one that would push the story of the field in a direction nobody anticipated. Because in that same miraculous year, Einstein published not just special relativity, but another paper, one that would eventually win him the Nobel Prize, and it had nothing to do with relativity. It was about light, and it suggested that Maxwell's beautiful wave theory of light was missing something fundamental. The paper was about the photoelectric effect, a phenomenon that had been discovered by Hertz himself and had been puzzling physicists for years. When you shine light on certain metal surfaces, electrons get knocked loose. That much was understandable. The light carries energy. The energy dislodges electrons. But the details were all wrong. Classical wave theory predicted that the energy of the ejected electrons should depend on the intensity of the light, on how bright it is. A brighter light means a bigger wave, which should deliver more energy to each electron. But that is not what happened.
The energy of the ejected electrons depended on the color of the light, on its frequency, not on its brightness. You could shine a very dim ultraviolet light on a metal surface, and electrons would fly off immediately. But you could blast it with an intense beam of red light all day, and not a single electron would budge. No delay, no build-up. Either the frequency was high enough and electrons appeared instantly, or it was not, and they never appeared, regardless of brightness. Einstein proposed a breathtaking explanation. He said that light is not just a wave. It comes in discrete packets of energy, particles, which he called light quanta, and which we now call photons. Each photon carries an energy that depends only on the frequency of the light, nothing else. A single ultraviolet photon has enough energy to knock an electron free. A red photon does not, no matter how many of them you throw at the surface.
100 million red photons cannot do what one ultraviolet photon can, because each interaction is one photon hitting one electron. And if the individual photon does not carry enough energy, no number of them will help. Now think about what this means for the field in the gap. Maxwell's equations describe light as a continuous wave of oscillating electric and magnetic fields. Smooth, flowing, filling space. And that description is correct. Light diffracts, it interferes, it polarizes, it does all the things that waves do. But Einstein was saying that light also comes in particles, in discrete packets, not instead of being a wave, also, both at the same time. The electromagnetic field, that invisible something filling the space between things, was turning out to be stranger than anyone had imagined. It was not just a smooth, continuous medium. It had a granular structure at the smallest scales. It was both wave and particle, both continuous and discrete, both spread out across space and concentrated at a point. This was the beginning of quantum mechanics. And it would take another 2 decades for physicists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others to build the full framework. But the electromagnetic field was at the heart of it from the very beginning. Every time an electron jumps between energy levels in an atom, it emits or absorbs a photon, a quantum of the electromagnetic field. Every chemical bond, every color you see, every signal running through your nervous system, it is all electromagnetic interactions happening at the quantum level. And here is where the story reaches its deepest, most surprising layer. Because the quantum understanding of the field reveals something that would have astonished Faraday, amazed Maxwell, and probably unsettled even Einstein, who never fully made peace with quantum mechanics. The empty space that everyone started with, the gap between the magnet and the ion, the void between the stars, the emptiness between the atoms in your body. It is not empty. It has never been empty. At the quantum level, the electromagnetic field is everywhere, always, even in the complete absence of any charges or magnets or light sources. The field exists in what physicists call its vacuum state, a state of minimum energy but not zero energy. It fluctuates, it trembles. Even in a perfect vacuum, at absolute zero temperature, with no particles and no radiation and no sources of any kind, the electromagnetic field is still there, still rippling with tiny, random, short-lived oscillations. These are called vacuum fluctuations, and they are not theoretical abstractions. They have measurable consequences.
The Casimir effect, first predicted in 1948,
and experimentally confirmed in 1997, is a real, physical force between two metal plates placed very close together in a vacuum. The force exists because the vacuum fluctuations of the electromagnetic field between the plates are constrained by the plate's presence, while outside the plates, they are unconstrained. The imbalance creates a net pressure that pushes the plates together. Empty space is pushing them. Or rather, the field in empty space is pushing them, because the space was never really empty. By the late 1940s, the full quantum theory of the electromagnetic field had been worked out. It is called quantum electrodynamics, or QED, and it was developed independently by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. QED describes every electromagnetic interaction as an exchange of photons between charged particles.
When two electrons repel each other, they are exchanging virtual photons. When a magnet attracts iron, the interaction is mediated by photon exchange at the quantum level. When light bounces off a mirror, photons are being absorbed and re-emitted by the electrons in the mirror's surface. And QED is, by some measures, the most precisely tested theory in all of science. The development of QED in the late 1940s was itself a dramatic story. The theory, in its earliest form, kept producing infinite answers. You would try to calculate the strength of an electromagnetic interaction, and the mathematics would give you infinity. Obviously, the real world does not have infinite forces, so something was wrong. The infinities arose because the theory required you to consider interactions at every possible energy scale, including absurdly high energies where the theory's assumptions probably break down.
Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, working independently in 3 different countries, the United States, and Japan, all found the same solution. They developed a mathematical technique called renormalization that allowed you to systematically isolate and remove the infinities, leaving behind finite, measurable predictions. Feynman later said he was not entirely comfortable with the procedure, calling it sweeping the infinities under the rug. But the results were staggering. The most famous prediction of QED is the anomalous magnetic moment of the electron. Dirac's equation predicts that the electron's magnetic moment should have a specific value related to its charge and mass. But QED adds tiny corrections to this value, arising from the electron's interaction with virtual photons in the quantum vacuum. The electron emits and reabsorbs virtual photons constantly, and this process slightly alters its magnetic properties.
The QED prediction for this correction, calculated to 10 decimal places, matches the experimentally measured value to 10 decimal places. The agreement is often cited as the most precise prediction in all of science. Think about what that means for the field in the gap. The electromagnetic field is so real, so precisely described by our equations, that we can predict its effects on individual particles to an accuracy of 1 part in 10 billion. The field is not a metaphor. It is not an approximation. It is one of the most precisely verified features of physical reality that human beings have ever measured. And the virtual photons, those fleeting quantum fluctuations of the electromagnetic field that contribute to the electron's magnetic moment, they are everywhere. Right now, in the space around you, in the air between your hand and the wall, in the empty space between atoms, the electromagnetic field is fluctuating. Virtual photons are popping into existence and vanishing again in intervals too short to measure directly, but their collective effect is real, measurable, and confirmed by some of the most precise experiments ever conducted. The vacuum, the thing we call empty space, is actually the ground state of the electromagnetic field. the lowest energy configuration of an invisible, omnipresent something that fills every cubic inch of the universe. And that ground state is not zero. It has energy, it fluctuates, it has structure. Space itself, empty space, is alive with the quiet trembling of the electromagnetic field. Its predictions match experiments to roughly 10 decimal places. To put that in perspective, it is like predicting the distance between New York and Los Angeles and being accurate to within the width of a human hair. All of this, all of quantum electrodynamics, is about the field. The electromagnetic field, the invisible something that fills the gap.
And that brings us to where we are now. The electromagnetic field, the invisible something in the gap, is the foundation of nearly everything in the modern world. When you flip a light switch, you are completing a circuit that allows current to flow through a wire. And that current heats a filament or excites atoms in a gas, or drives electrons through a semiconductor, all of which produce photons, quanta of the electromagnetic field, that travel from the bulb to your eye at 186,000 miles per second. When you make a phone call, your voice is converted into electrical signals, which are used to modulate electromagnetic waves that radiate from the phone's antenna, travel through the air to a cell tower, are relayed through fiber optic cables where the signal travels as light, another form of electromagnetic wave, and arrive at someone else's phone, where they are converted back into sound waves that their ear can hear.
The entire chain, from your voice to their ear, is electromagnetic. When a doctor orders an MRI scan, the machine uses superconducting magnets that produce a magnetic field roughly 60,000 times stronger than the Earth's natural field. That field aligns the spin of hydrogen nuclei in the patient's body. Radio frequency pulses, electromagnetic waves, are then used to disturb those spins, and when the spins relax back to alignment, they emit their own radio frequency signals, which the machine detects and assembles into a three-dimensional image of the body's internal structure. The entire process, from imaging to diagnosis, depends on the electromagnetic field and its interaction with the quantum spins of individual atomic nuclei. When you use Wi-Fi, your router is broadcasting electromagnetic waves at a frequency of about 2.4 or 5 billion cycles per second.
Those waves carry data, encoded as patterns of amplitude and phase variation, ripples in the electromagnetic field that your laptop's antenna detects, decodes, and turns into the web page or video you are watching. The data travels through the air, through walls, through furniture, riding on the same electromagnetic field that Faraday imagined and Maxwell described. And here is something that connects all the way back to where we started. Back to the question of what fills the gap. Every one of these technologies depends on the field being real. Not a metaphor, not a mathematical trick, not a convenient way of thinking about forces. Real. The radio waves carry real energy. The MRI machine manipulates real quantum spins. The light from your screen is real photons, real quanta of the real electromagnetic field, hitting real photoreceptors in your real eyes. If the field were not real, if the space between things were truly empty, none of this would work.
Radio signals could not travel from a transmitter to a receiver because there would be nothing to carry them. Light could not travel from the sun to the earth because there would be no medium to propagate through. Your phone could not receive a signal because there would be nothing connecting it to the cell tower. The field is the medium. The field is the connection. The field is what fills the gap, and it is what makes the modern world possible. And the field is not just around you, it is in you. Your nervous system is an electromagnetic machine. When a nerve cell fires, it generates a brief pulse of electric potential that travels down the nerve fiber, a wave of depolarization, ions flowing through channels in the cell membrane, creating a tiny electric field that propagates at speeds of up to about 390 feet per second in your fastest nerve fibers.
Every thought you have, every movement you make, every sensation you feel is carried by electromagnetic signals running through your body. Your heart beats because of an electrical impulse generated by a cluster of specialized cells in the right atrium, the sinoatrial node, that sends an electromagnetic signal spreading across the heart muscle, triggering each region to contract in the right sequence. If that signal gets disrupted, if the electrical pattern becomes chaotic, the heart can stop pumping effectively. And one of the ways doctors restore the rhythm is with a defibrillator, a device that delivers a powerful pulse of electrical energy to the heart, essentially resetting the electromagnetic pattern so that the normal rhythm can re-establish itself. Even at the atomic level, the electromagnetic field is what holds you together. The atoms in your body are stable because electrons are bound to nuclei by electromagnetic attraction. The chemical bonds between atoms, the bonds that build proteins and DNA and cell membranes and bone, are electromagnetic. When a molecule absorbs energy and changes shape, when an enzyme catalyzes a reaction, when a photon of light strikes a photoreceptor in your eye and triggers a cascade of chemical reactions that your brain interprets as vision, all of it is the electromagnetic field at work. You are not separate from the field. You are an expression of it. A temporary, beautiful, self-aware pattern in the electromagnetic field, held together by the same force that pulled iron toward a lodestone in ancient Magnesia. So let us come full circle. Let us go back to where we started, to that gap between a magnet and a piece of iron. What is in that gap? The answer, after 25 centuries of wandering, after lodestones and amber and sparkling machines and Leyden jars and kites in thunderstorms and twitching frog legs and voltaic piles and compass needles twitching near current-carrying wires and iron filings tracing invisible curves and equations written in a quiet Scottish study and sparks jumping across laboratory detectors and light bending through space and photons exchanged between charged particles in the quantum vacuum. The answer is the electromagnetic field. It is there, right now, in the room where you are lying. It is in the walls around you, in the air above you, in the pillow under your head. Radio waves from stations you have never listened to are passing through your body at this very moment. The faint magnetic influence of the Earth is gently nudging every compass needle within 1,000 miles. Infrared radiation is radiating from your own skin. Photons of the electromagnetic field carrying your body heat away into the room. The electric signals running down your nerves, the ones letting your brain turn these sounds into meaning, are electromagnetic too. Ions flowing through channels in your nerve membranes, creating tiny electric fields that propagate from cell to cell at hundreds of feet per second. You are surrounded by the field. You are permeated by the field. You are, in a very real sense, made of the field, because the atoms in your body are held together by electromagnetic forces, electrons bound to nuclei by the same force that made a lodestone pull iron in ancient Turkey. The field is the reason light exists, the reason chemistry works, the reason your phone can pick up a signal from a tower miles away, the reason an MRI machine can image your brain, the reason a compass points north, the reason your heart beats in rhythm, the reason you can see the face of someone you love. And maybe the most remarkable thing about the field is how long it took us to even notice it was there. For 2,000 years, we looked at the space between a magnet and a piece of iron and saw nothing. We saw emptiness. We saw a void. And the whole time, that space was full of something that carries energy, transmits force, propagates waves, and holds atoms together. Full of the invisible architecture of nearly everything we experience. Faraday saw it first. He could not prove it mathematically, but he saw it. He looked at the space around a magnet and said, "That is not empty. Something is there." And Maxwell proved him right, in the most beautiful way imaginable, by writing 4 equations that captured the entire behavior of the field and predicted that it could carry waves at the speed of light. And now, tonight, that field is doing its quiet work all around you. Light travelled from distant stars to reach your window.
Radio waves slipped through your walls without you noticing. Your phone received data carried by electromagnetic waves, oscillating billions of times per second. The electrical signals in your brain processed those signals and turned them into thoughts and feelings, and the soft, heavy sensation of approaching sleep. The field does all of this. It has been doing it since long before anyone knew to look. Since long before Thales picked up a lodestone and wondered why iron jumped. Since long before the first human eye opened and light entered it. The field was there in the beginning, filling space, carrying light from the first stars, governing the first chemical reactions, shaping the first atoms. And the people who figured it out, who peeled back the layers of the mystery over those 25 centuries, they were real people. Flawed, brilliant, stubborn, sometimes lucky, sometimes wrong, always curious. Thales, who thought a stone had a soul. Gilbert, who carved magnets into tiny earths and proved the whole planet was magnetic. Franklin, who pulled lightning from the sky with a kite and a key. Galvani and Volta, who argued about frogs and accidentally invented the battery. Ørsted, who noticed a compass needle twitch during a lecture. Ampère, who worked out the mathematics in a single fevered week. Faraday, the bookbinder's apprentice who never learned calculus, but who looked at empty space and saw it full. Maxwell, the quiet boy from Scotland who asked, "What's the go of that?" until he had written the equations that described the universe. Hertz, who caught the invisible waves in a laboratory and said they were of no use whatsoever. Einstein, who looked at Maxwell's equations and saw that space and time themselves had to bend to accommodate the speed of the field. These are all real people. And the thing they uncovered, piece by piece, mistake by mistake, surprise by surprise, is the invisible architecture of your world. It was always there. They just taught us how to see it. And then there is one more layer to the story, perhaps the deepest one of all. And it answers a question you might not have thought to ask. Why does the electromagnetic field exist at all? Physicists in the 20th century discovered that the existence of the electromagnetic field is not arbitrary. It is not a random feature of the universe that just happens to be there. It is required by a symmetry. A deep, mathematical symmetry in the equations that describe matter. In the 1920s and 30s, physicists developed a description of matter at the quantum level, called the Dirac equation, that describes how electrons behave. And this equation has a curious property. You can shift the quantum phase of the electron, a kind of internal clock that has no directly observable effect, by the same amount everywhere in space, and the equation does not change. The physics stays the same. This is called a global symmetry.
But what if you want to shift the phase differently at different points in space? What if you want the symmetry to be local, meaning You can change the phase by different amounts at different places. That breaks the Dirac equation. The physics changes. The equation stops working, unless you introduce a new field. A field that adjusts itself to compensate for the varying phase shifts. A field that smooths things out. A field that restores the symmetry. And when you work out what properties this compensating field must have, what equations it must obey, you discover that it must be exactly the electromagnetic field. It must be a massless field carried by a massless particle. It must produce forces on charged particles according to the Lorentz force law. It must obey Maxwell's equations. The electromagnetic field is not optional. It is demanded by symmetry.
If you want the laws of physics to have a certain natural, elegant symmetry, if you want the freedom to redefine your quantum phases at each point in space independently, then the electromagnetic field must exist. The photon must exist. Maxwell's equations must hold. This principle, called gauge symmetry, is one of the deepest ideas in modern physics. And it applies not just to electromagnetism. The same logic, the same principle of local symmetry demanding the existence of a compensating field, explains the other fundamental forces of nature as well. The weak nuclear force and the strong nuclear force both arise from their own versions of gauge symmetry. More complicated symmetries involving more complicated fields, but following the same basic pattern. So the electromagnetic field is not just a convenient description of how magnets and charges behave. It is a necessary consequence of the mathematical structure of reality.
It has to be there, the way the number 3 has to be between 2 and 4. It is built into the logic of the universe. And that, perhaps, is the most remarkable answer to the question of what fills the gap between the magnet and the iron. The electromagnetic field fills it. And it fills it because the universe has no choice. Symmetry demands it. The deepest principles of physics require it. The field is there because it must be there. It is as fundamental as space and time themselves. So as you lie here, maybe drifting, maybe already half asleep, let this thought settle in. You are resting inside a field. The electromagnetic field fills the room, fills the building, fills the sky, fills the space between the stars. It is carrying signals and light and warmth through every inch of the darkness around you. It is holding the atoms of your body together. It is running through your nerves, beating your heart, firing the last quiet thoughts of the day across the synapses of your brain.
And that gap, the gap between things, the space that looks like nothing, it was never nothing. It was always full, full of the most extraordinary something that anyone has ever discovered. A something that is everywhere, always, invisible but never absent, quiet but never still. And here is one last thought to carry with you. The electromagnetic field is not just the most well-understood force in physics. It is also, in a sense, the most intimate. You interact with gravity at a distance, feeling the pull of a planet millions of miles below your feet. You interact with the nuclear forces only through the particles they bind, never directly. But the electromagnetic field touches you, literally. Every surface you feel, every texture under your fingertips, every pressure against your skin is the electromagnetic repulsion
between the electron clouds of your atoms and the electron clouds of whatever you are touching. You have never truly touched anything in your life.
The atoms of your hand and the atoms of the table never make contact. They are always separated by a tiny gap, a gap filled with the electromagnetic field, pushing back, keeping the atoms apart, giving you the sensation of solidity. The gap was never empty. Even the gap between your hand and the things you touch is full of the field. And it is that field, that invisible presence, that gives you the experience of a solid world. The field is there. It has always been there. And right now, as you rest, it is doing what it has always done, holding the world together, carrying the light, filling the silence with a presence you cannot see, but that touches everything. You do not have to hold on to any of it. You do not have to remember the equations or the names or the dates. They will be there in the morning. The field will still be humming along, quiet and everywhere, doing what it does. For now, just rest. Let the field do its work. Let the invisible architecture hold. Let the light travel and the waves ripple and the atoms cohere and the silence fill with all the things you cannot see. The gap was never empty, and you were never alone in it. The field is there. Sleep well.